Hello and welcome to lecture number 17. So in the next lecture, that is in lecture the lecture concerned on next topic, we will focus on the gas solid interface. So today we are going to talk about the contact angle. So that means the angle that a liquid essentially makes with a solid. So therefore we have to talk about solid liquid interface, and while talking so, obviously the liquid gas and the solid gas interface would come into picture. So the contact angle of a liquid on a solid surface is a very important topic, and it also involves cohesive and adhesive forces. So we will see today that how a measuring contact angle would define the three interfaces, that is solid liquid, solid gas and liquid gas. So first let's start with the estimation of surface tension, or in other words the surface energy of a liquid from capillary rise method. Remember, there are two or three important methods for determining the surface tension of a liquid, and capillary rise method is definitely one of them. Now, why we would be talking about the capillary rise method? Because there are one single very important reason that a liquid inside a capillary, for example water inside a glass capillary, makes a curved surface. Okay, so when it interfaces with air, and that has very serious implications. And also that curvature helps us to determine the gamma, that means the surface energy. So imagine we have a capillary dipped inside a reservoir, and the radius of curvature is r. All right. So now we all know water makes a concave surface upward, right? So this is my liquid side, and the upward is air, so we just call it gas. And let's assume the radius of curvature is r. All right. So definitely, since this is a curved surface, so there would be a pressure difference between point A and point B. So what is the pressure difference? The pressure difference we straight away write from the Young Laplace equation, you remember, 2 gamma prime divided by r. So why we are taking gamma prime, not exactly the gamma? Because since the liquid curves in a concave manner, and at the point of contact here, if we draw a tangent, so the surface tension actually works along the tangent ideally. So therefore, if we are talking about the actual component that is responsible for holding the surface molecules, that means its effective surface tension is actually working in this direction, and this is gamma prime, and this actually equal to gamma cos theta. So therefore, this pressure difference would be written as 2 gamma cos theta divided by r. So the theta is defined, the tangent makes the angle that is made between the tangent and the point of contact with respect to the vertical glass wall. So theta is called the contact angle. Okay. So now here we see if the surface is concave, the theta is less than 90 degrees. So that means the cos theta is positive. So now let's quickly balance that this pressure difference must be balanced by the hydrostatic force. So that means the rise, the total rise of the capillary. So this hydrostatic force is given by the volume of the liquid, all right, and multiplied by the density, and multiplied by the acceleration due to gravity, all right. So therefore, this pressure difference, that means delta P, is balanced by, this is equal to H rho G. All right. So where H rho g is the hydrostatic pressure, rho is the density of the liquid. So from this relationship, we can easily find out what is the expression for gamma here. Expression for gamma, therefore, gamma is equal to R H rho g divided by 2 cos theta. All right. So by following this, measuring the angle theta and the capillary rise h and knowing the radius of the curvature, so the R is such that the width of the capillary is actually twice of R. So knowing the rho and g is already known, and the R, we can actually determine the surface tension gamma. All right. Now, one important thing is there, this gamma is the surface tension, or that means the interfacial tension of liquid and gas. So therefore, we can also rewrite this expression as gamma. So we take L as liquid and V as vapor. Okay, assuming that it is not vacuum, so it should be gas, means the moisture of the water. So we call it LV, gamma LV is equal to R H rho g divided by 2 cos theta. So now let's remember this equation. All right. So it will come handy later on. So now let's try to appreciate one fact, that when theta is actually greater than 90 degree, we have cos theta negative. So whenever we have cos theta negative, the curvature goes the opposite direction. So that means the curvature becomes convex. Okay, so we have a more than 90 degree contact angles, and we actually see it in case of mercury. So if we have a mercury reservoir, all right, so the mercury would behave like this, and inside the capillary, the mercury is, instead of elevation, the level of the mercury, meaning the surface of mercury, would undergo depression. All right, so it will fall below the reservoir height. Okay, and it can be all explained from the negative contact angle. So now let's try to address one important question, that how high can water climb up the walls of a clean glass surface. So remember, by this question, I'm not asking that how high the water can climb up due to hydrostatic force, because that is related with the H is inversely proportional to rho. So if the narrower the capillary, the higher is the rise of the water. So I'm not asking that question. I'm asking something like this. So I am drawing it. So remember, what I'm drawing is, say this is the horizontal line, and we have a curved surface like this, and this elevation at the side is denoted as L. So my question is that how far water can rise from the horizontal line. Okay, so how far water level can climb up the walls of a clean glass surface, L. So by some numerical methods, okay, like Rourkela method or something else, it has been possible to estimate. So this elevation L can be represented as root over of gamma divided by rho g. And for water, this L is actually in the range of few millimeter. Okay, and in fact, for water, the maximum value it can take under all everything is well optimized, in that situation is maximum up to 4 millimeter. All right. So because it is balanced by the density and the gravitational force and etc., etc. So this is the maximum it can actually rise. So now the question is, why does the water molecule would creep up through the glass wall? So why don't we see depression, like why for water, why don't we see something like this? For mercury we see something like this, but for water we see its elevation, and for mercury we see depression. And there are some liquids may not for which the elevation, neither the elevation nor the depression will be that much pronounced. The question is why? What is the molecular reason that we must see this? All right. So some important concepts are hidden with this simple in explaining this simple observation. So let me clean the board and let's try to explain or answer that question, that why does a liquid climb up the walls of a glass surface. All right. So we can explain the rise of the liquid edge at the capillary like this. If we take a look, or if we look at the incident from a molecular perspective. So this is the solid surface. So now if we assume that the liquid creeps up, so that means at the point of contact, so we see that there is an interactive force between these liquid molecules versus the solid molecule. So this force that is acting between two different kinds of molecules, the molecules of liquid and the solid, we call that force as a cohesive force or cohesive energy. So it's adhesive force or adhesive energy. And the force between two same type of molecule, we call it cohesive force or cohesive energy. Now we can explain the rise of the liquid is that basically the adhesive force is more pronounced than the cohesive force. That's why the more number of molecules tends to be in contact with the solid surface than with the other the same kind of molecule. And if the adhesive force is very much supersedes the cohesive force, then the liquid tends to wet the glass. All right, and we call the liquid as a wetting liquid. And if it goes the other way, so that means the liquid doesn't want to be in contact with the surface, we call the liquid as a non-wetting liquid. So but there is a bit better understanding or better explanation in terms of surface energy to explain the phenomena. So what I have drawn are two diagrams. So in the left we have a relatively non-wetting liquid, and on the right we have relatively more wetting liquid. So when we shift from a less wetting to a more wetting liquid, so that means the liquid molecules are creeping up through the surface or along the surface. So here, compared to this picture, if we concentrate on this picture, you see we have, so if that is the total portion of the solid surface is in question, so from this to there we see less interface facial area available between vapor and solid, and more interfacial area available between liquid and solid. So we can write that in this case the interfacial area between solid and liquid is more than the interfacial area of solid and vapor. All right. So how is it possible, if we try to explain in terms of surface energy, interfacial energy. So we knew that whenever a surface tends to expand, the surface tension has to fall. So right away, from our knowledge on surface and colloids, we can simply say, then in this case, it must be true that the interfacial energy, that is the gamma LS or SL, okay, gamma solid liquid, must be less than the gamma solid vapor. So, if this condition is fulfilled, this is only when the liquid molecules would climb up the up along a clean, capillary glass surface or glass wall. All right. So now we will try to establish a relationship between these three factors, that is gamma SL and gamma SV, and there is another thing, that is gamma solid vapor. Sorry, the liquid vapor, gamma LV. Yes, gamma LV. So, how to establish the relationship? So, for that, we have to come back to our the capillary rise situation for water inside a glass capillary. So, the water will rise inside the capillary. So let's assume the total height elevated due to the hydrostatic pressure is H. And so let's not forget that before we dip the capillary, the surface is over here, okay? So the entire volume was here. And then once we dip the capillary, some amount of liquid climbed up, all right? So effectively, the center of gravity for the volume of liquid placed inside the tube has been elevated by h by 2. So therefore, now at this position, the situation is at equilibrium. So that means the liquid is not more climbing up anymore, the liquid is no more dropping down. So it is in equilibrium, and it is at the constant temperature. All right. So the potential energy increase is can be defined as the pi r square h, the volume multiplied by the density multiplied by the acceleration due to gravity, so here h part will not be here, so my mistake here. So pi r square rho g h by 2. So this is the mass G multiplied by G. So this is basically the weight of the liquid through which the potential energy increases, and this should be balanced by the surface energy decrease. So surface energy means the total amount of liquid present, that means the liquid in contact with the entire surface of the capillary. So that means we have to estimate the if this is the capillary, okay, so whatever this is the liquid, so whatever the total point of area of contact means the cylindrical area, so that can be defined as 2. So if the radius of the capillary is r, so 2 pi r multiplied by height elevated h, 2 pi r h, and then there would be the surface tension or surface energy factor. But what factor we should put here? We should put here the surface energy would decrease by the amount when the higher interfacial energy is replaced by some lower interfacial energy. So therefore, the difference would tell me that gamma SV minus gamma SL. All right. So at equilibrium, the total free energy GT should be equal to this minus this. All right. So I'm just writing in short that PE increase minus surface energy decrease. All right. So now at equilibrium, this change in GT with respect to the height h must be equal to 0. So or we can write that d gt dh is equal to 0. So if we instead of gt, if we put this expression over here, so that means basically we have to plug in this equation here, and if we take the first derivative with respect to h, then if we do that, if we do the simple maths, then we will come back to an expression something like gamma sv minus gamma sl is equal to rho g h. All right, rho gh divided by so the r will be there. Okay, so r rho gh divided by 2. Okay, yes, r rho gh divided by 2. So now this r rho gh divided by 2 can be easily replaced by gamma LV, because as I told you while we were discussing the method of estimating gamma LV through capillary rise, then we had an equation, all right, so that gamma LV is equal to something divided by twice of cos theta. So if we follow that equation, so this equation can be replaced by gamma LV cos theta. All right, so this value came from the capillary rise equation. So the same thing can be applied, because since we are actually dealing with the capillary rise of water inside a glass capillary. Okay, so therefore it tells me that we have a new equation, gamma SV minus gamma SL is equal to gamma LV cos theta. All right, so this equation is known as Young's equation. So this is the Young equation, not Young Laplace equation. So this is a bit different one. So we had the Kelvin equation and Young Laplace equation, and this is pure Young's equation, or simply Young equation. So this Young equation has some deep implication in terms of surface science and interfacial energy, and the application of this equation is actually quite interesting, as we will see later that it is applied to explain certain very interesting phenomena. All right, so in the next part of the lecture, let's try to discuss this Young's equation a little bit more detail, and what are the different implications of this equation. All right, so let's clean the board and continue. Okay, so this is the Young's equation I have written once again, and the question is, so how to appreciate the different types of interfacial energies here. So gamma SV, gamma SL, and gamma LV. Well, the theta part can be measured from the contact angle. So now the thing is gamma SL. So we are interested to know gamma SL. So gamma SL can only be known if we know the gamma LV and gamma SV. Now gamma SV or gamma LV is relatively easier to measure. Okay, so because there are several methods to measure the surface energy of a liquid. Now the question is how to measure gamma SV. Well, the answer is the measuring gamma SV is very difficult. Okay, so there is no direct method we can do. We can estimate gamma SV indirectly by creating a new surface. For example, you see, let's imagine that this is a solid block, and if we just make two new surfaces, then the energy required to make the two new surfaces would be indicative of the gamma S. That means the surface energy of the solid. But once again, making two new surfaces is not easy. Remember, we are not talking about snapping or breaking. We have to produce two molecularly smooth surfaces. All right, so then only we can have two completely new surfaces. So and it only happens for few classes of materials. So practically it is not possible to create two ideal surfaces from a current solid, because we are not in a process of just breaking it. Breaking would create some uneven surfaces. So that's the point, and we can't also cut it. Okay, so cutting may not be molecularly smooth. So, but for certain materials, we can do so, and if we do so, then we are talking about cohesive energy per unit area WC, which is actually twice of the gamma SV. All right. So, and obviously we are making two new surfaces, so this cohesive energy per unit area would be twice of these two new surface, hence surface tensions. So twice of gamma SV. So if the outside is vacuum, means the vapor is actually nothing but vacuum, then this twice of SV can be go close to gamma S. All right. So and that tells us that in vacuum, okay, so gamma S is equal to gamma S. We have some estimation on the solid's surface energy. But once again, it's just an estimate for certain materials. For any material in general, it cannot be directly measured. All right. So therefore, we are in a situation that gamma SV cannot be directly measured, and also gamma SL cannot be directly measured. Only we can measure this part. So what next? We'll come to that later. But before that, since we are talking about cohesive energy, in contrast, we can talk about adhesive energy. So the adhesive energy, once again, per unit area, can be expressed in terms of gamma A plus gamma E minus gamma AB. So here A and B is actually relating to the two different surfaces. So if we can think about the reverse, so this is the material A and this is the material B. So when we try to join the two surface, the adhesive energy gamma A, WA becomes the gamma A, means the surface energy of A plus surface energy of B minus gamma AB. So there is also a definite mathematical expression for gamma AB. So we're not coming into that. But there is a catch. So once again, how to measure, estimate this adhesive energy? Because adhesion, if you talk about the adhesive energy, so adhesion, it doesn't mean that we just join A and B and can compress and the surface goes out. Means there is no existence of that previous surface. No, it doesn't happen in that manner. So why? So let me erase that and explain to you. So I'll try to explain the adhesive energy once more in somewhat more detail. So there are two surfaces where we have surface energy. For one substance is gamma A and for other is the gamma B. And then if these two segments are joined together, then somehow in the resulting material, the interface would vanish. So that means there would be no demarcation. So no one can identify that, okay, this was the interface previously. So it has to be joined uniformly with molecular smoothness. That is the definition of adhesion. All right, so that means you won't be able to distinguish the two molecules right at the interface. That means molecule from substance A and molecule for substance B. You cannot make a distinction that still there is some difference line. So mathematically WA is defined like this. and where gamma AB is called the interfacial energy between the solids in contact. But once again, gamma WA is difficult to measure because we need molecule to molecule contact, and let's remember that this addition works based on the intermolecular forces. So unless there is some covalent bond, the addition works based on van der Waals forces. Now for these intermolecular forces are really short range. So this is 1 raised to the power of r to the power minus 6. So inversely proportional to the r to the power 6. So therefore you need to have a very close and intimate molecular contact. So simple pressing doesn't always give you the adhesion. Alright, so simple pressing does not give you adhesion, but it works on certain substances. For example, mica. So the mica surfaces are so smooth that if we can press the two mica segments, that it is possible to erase the distinction of the interface, and the two different segments can behave as one single piece. But it is only possible in case of mica, where by putting physical pressure one can have intimate molecule to molecule contact. So therefore, what was the greatest problem? So the greatest problem is, here we can say that by pressing we cannot have adhesion because the actual contact area would be less than the geometrical contact area. Okay, so that means substance has to be molecularly smooth. So geometrical area means the actual area that is we are talking about, means the total area, geometrical area. So means the total area in question. Now actual contact area means, we would call that actual contact, where all the molecules from one surface should be touching with each and every molecule. Means each molecule of one surface should touch individually the molecules of the other surface. So that's what we call an intimate molecular contact. So that's why simple, except for mica, this addition through simple pressing cannot be achieved. All right. So you see, this addition is indeed a little bit more complicated than is normally thought of. So we need a facilitator to have an addition. So this facilitating agent is called the glue. All right. So what is the scientific definition or purpose of the glue? So the glue actually facilitates the intimate molecular contact. So what it does, actually, it increases the probability of the two different molecules from two different substances to come close to each other. So that's the purpose of the glue. So the glue would provide one more interface, so that through that interface the molecules of two different surfaces can come into much more molecularly uniform contact compared to when we are just putting two pieces together in absence of the glue. All right, so you see that the function, the glue, the substance itself and its function are all related with surfaces and interfaces. All right, so now we have a little bit idea about the cohesion, adhesion, and how these cohesive forces and adhesive forces work in terms of surface and interface. All right, so now we'll come back to the original discussion topic that we started on before we come to this topic, that is the practical implication of the Young's equation. So let's go back to and start discussing that Young's equation once again. All right. Okay, so since the cos theta part is an important aspect in Young's equation, and since theta stands for the contact angle, So therefore, contact angle plays a huge role to estimate the surface energy of the solid. So measuring the contact angle made by a liquid on a solid surface, we can estimate the surface energy of the solid. So how we can do that? So that's what we are going to explain. So you see, I have drawn three different kinds of liquids here. So on my left, I have an example of a wetting liquid. And so this is one extreme case. All right. So that means the liquid is extremely wetting. So it is spreading almost all over the surface. Now in my right hand, it is another extreme case. All right. So we have a non-wetting liquid, and the liquid, you see, is trying to minimize the area of the contact with solid. So here we have the largest contact area, we have the smallest contact area. And you see the theta angle, the contact angle, if I draw it like this, the theta is very small, so theta almost tends to 0 degree. And here you see theta is more than 90 degree. So somewhat in between, I have drawn an intermediate picture. Okay, so where the wettability of the liquid is medium, moderate. So there we have drawn it in such a manner that theta is less than 90 degrees. So therefore, this is how we can define theta, the contact angle. This is the liquid phase, solid phase, and vapor phase. So now, of course, in solid liquid interface we have the gamma SL. In solid vapor interface, we have this gamma SV is active, and on vapor liquid interface, we have gamma LV is active. So now you see at this point, the point that I have circled it out here, at this point, all the three phases are at equilibrium. So this is a three-phase equilibrium point. All right. Now, since this is a two-dimensional diagram, so we can think of it as a point, but the moment we can think about the three-dimensional thing, so there will be many more points where the three-phase equilibrium exists. So therefore, we can easily imagine that there exists an infinitesimal length, that is dl, where all the three phases are at equilibrium, assuming that temperature is constant and the surface is clean and smooth. So if we apply the assumption, and if we apply the concept of minimization of free energy like we did before, once we tried to derive the Young's equation. So if we apply the concept of minimization of free energy on that infinitesimal length dl, where all the three phases are at equilibrium, then it is possible to show, to derive the same Young's equation. So which comes down to gamma SV minus gamma SL is equal to gamma LV cos theta. All right. So we would come down to the same equation. So this is known as the Young's equation. So interestingly, if we draw a kind of a vector diagram, so if we draw a diagram like this, two vectors lying at a mutual angle of 180 degree, and this is a theta. And if we draw vectors like this, so this is gamma SL, this is gamma SV, and this is gamma LV. So from the rules of the vector addition, the same formula, that is the Young's equation, can be proved. So interestingly, now we would see that how from this Young's equation one can estimate the surface energy of the solid. Mind that, because we have already an idea of how to measure the surface energy of the liquid. So there are methods. Capillary rise method is one of them. So now we're interested to know the surface energy of the solids, and this Young's equation would help us to have an estimate on that. But for that, we have to apply certain conditions and certain assumptions. So how we do that? So let's erase this part and let's write it here to explain more. So now, this is the Young's equation. Now interestingly, let's assume that there exists a liquid where theta is equal to 0 degree. So that means we are thinking about an extremely wetting liquid. So in an extreme case scenario, we have the liquid spreading so efficiently that it is covering almost all the surface. So when theta tends to 0 degree, so if we just try to measure the angle theta, so this theta is so small that we can assume that theta is tending to 0 degree. So when theta tending to 0 degree, obviously cos theta tends to 1. So at that situation, we can have gamma SV minus gamma SL is equal to gamma LV. Alright? But you see that when we have such a scenario, now think about the topic that I started with, that we can have the liquid spreading all over the surface in only one case where the gamma SL should be less than gamma SV. So that means for liquid to spread, the interfacial tension between solid and liquid should decrease so that the liquid can relax its interface and spread all over the surface. So therefore, in this particular case, when theta tends to 0, we have to assume that this gamma SL tends to 0, or the gamma SL is so low that we can safely neglect with respect to SV. So therefore, we can write that when theta tends to 0 degree, we have gamma SV almost is equal to gamma LV. So there is an assumption that gamma SL is 0, and this is a safe and practical assumption, is equal to LV, and that is equal to a whole new quantity, and we call it gamma C, and that stands for critical surface energy of solid. So that means for a particular kind of solid, there should be at least some liquid. If it spreads all over from that situation, we can guess the critical surface energy, where the critical surface energy is nothing but the gamma solid vapor interface, and which becomes almost equal to the gamma liquid vapor. So that is the basically the way to understand and explain the critical surface energy. And the thing is, that is the only way we can measure, and we cannot directly measure either gamma SV purely. All right, so that's the problem. So in direct manner, we can have an estimation of the critical surface energy. Remember that may not be the actual surface energy of the solid, but it gives an estimation based on a critical scenario where any liquid can have a 0 degree contact angle. Now, how to practically estimate gamma C? For that, we can have a graph plot. So we have to take a solid, any solid, all right? And for this solid, we will try different kinds of liquids. So for example, we have the same surface, but we try different liquids, A, B, C, and D. So we'll start with liquid A. So first there will be a contact angle theta, and then we pick up another liquid. So again, the liquid spreads a little bit more. So theta, once again, theta is less. And then once again, more kind of weighting liquid. And at the end, we get something like this. So this is even the most weighting liquid. So for that, we have like theta 1, theta 2, and theta 3 and theta 4. So here on the y-axis, we take the theta values, and these are the different liquids A, B, C, D. So therefore, in this side, we plot the gamma LV. All right. So therefore, we have different gamma LV. So gamma LV means basically it's the surface tension of the pure liquid. So we can go the different values. So here we can plot millijoule per meter, and here we have theta. Theta means we can also plot cos theta. All right. So the maximum value of cos theta here is 1, where theta is equal to 0 degree. So for all these theta, these are non-zero values. So we may have points like this. All right. So like this. So therefore, if we try to draw the best fit straight line, so it should be a straight line. And then if we just extrapolate these lines by simply extrapolating it, so the moment it actually cuts this cos theta value is equal to 1. So from that, we can directly estimate the value. So this value is actually gamma C, that is the critical surface energy. All right. So now one thing for sure from this data that whenever you have a waiting liquid, all right, you can see, so the gamma SV, effective gamma SV falls. I mean, it becomes lower, and it becomes lower to almost to the value of gamma LV, because usually gamma SV should be higher than gamma LV. But once you have another layer of liquid and solid, the gamma SV value tends to drop down, and it will drop until the value of the critical surface energy, where what I mean to say that on a solid surface, if we have a most waiting liquid like this, we have the least amount of critical surface energy, or in other words, the effective surface energy of the solid should come to a very low value. All right. Now this has a major practical application, major practical outcome. So the outcome is, if we have a solid, say glass, all right, again we have glass. So we have three scenario. So the upper phase is here we have vacuum, here we have air, and here we have water. Now in complete contact, right? So it is submerged below the water. So the effective interfacial energy, we can call it the critical surface energy for vacuum and glass. For this would be highest, okay, and in air almost the same as the vacuum. But once we go to the water glass interface here, due to the outcome of the Young's equation that we have just saw, so gamma SV, all right, would fall, and since water is a waiting liquid, it would fall appreciably small to become very close to the value of gamma water vapor interfacial. So that means it would become a value close to the interfacial energy of the water. So that means what? So that means in air, glass have high gamma, high interfacial energy, and in contact with water, glass has lower interfacial energy. So when I was young, probably I was in the high school, so I went to visit some science exhibition, and there I saw one very interesting demonstration. That is, one person, he took a glass sheet, like the glass panel, the transparent glass window panel you normally see on the windows. So that kind of glass sheet, and with a cloth cutting knife on the other hand. And he showed us that in air, he is unable to cut that glass with that cloth cutting knife. But then he demonstrated that the moment he submerged the glass piece inside water, and then he tried to cut the same glass with the same knife, he could do it very easily. And at that time he explained the reason. The cutting glass is easier under the water. Not even glass, for any solid substance, it is easier to cut it with interface in water. But at that time, it was beyond my understanding. But now, perhaps, from the explanation of Young's equation, hopefully now you can understand that why making incision or cutting glass or any other material inside water is so easier. And we actually apply it every day in day-to-day life. Remember, when we shave our beards, all right, so we actually wet our face. So you just think about our face is some solid and we are wetting it with water. Okay. So of course we can argue that we can use some soap water, so that some can argue that, well, if you do that, we actually reduce the friction of the between the blade and the skin. But definitely that is true. But more than that, the major reason that to shave the shaving on a dry face makes it difficult rather than shaving in a wet face is easier. The main reason that when we apply some water on our face, we are creating a water, or say this is the hair strands, facial hair strand. So we make a interface between the water and the facial hair strand. And hair strand is made of like proteins. So this is solid material, and it reduces the surface energy of that solid hair particle, and therefore it becomes easier for the razor to cut it rather than if we try to do it on the dry face or on the dry um, hair. So this is the reason that sometimes you go to the barber shop to shave off your head. And so the barber, before shaving it, the final stage, they apply a lot of water on your head, and it wets the hair, and then he tries to shave off. So the major reason is very scientific, because the barber is actually applying and the Young's equation in order to lower the surface energy of solid by putting it in contact with a wetting liquid, that is water. All right. So you see, so this part of this surface and interface had a little connection with our practical day-to-day life. So anyway, we stop it here. And so in next lecture, that is from lecture 18 onwards, we will start a new topic. This is the last topic of our course, that is the solid gas interface. All right, so stay put and study the lectures, and I will see you see you later. Okay, so goodbye.